Okay, in this lecture we're just going to talk a little bit about functions. So a fairly abstract way of thinking about functions is a function is something that associates to an input, an output. Um, and we've been talking about functions a little bit in this module. We spoke about matrices as functions where the input was a vector and the output was a vector. And we also spoke about operators earlier in this chapter where we said, for example, you can think of differentiation as a function where the input is a function and the output is a function. And we said we call it an operator because it's a bit confusing when you've got a function where the inputs are functions themselves. But anyway, just going back to functions of a single variable. So these are things where you put a number in and you get a number out. In an engineering context, you can think about these things as relationships between variables. And you can write y is equal to f of x or y is equal to y of x if the variable y depends on the variable x. So I've got a load of examples here. I probably won't go through all of them. You can have a little look through yourself. The area of a square is okay. So the area of a square is a variable. The side length of the square is another variable, and there's a relationship between these two. So you could say that area is a function of side length. In terms of inputs and outputs, the input is the side length and the output is the area. And when you're graphing these functions, in fact, a graph of functions is defined as all the points of the form input, output. So for example, 3 in, 9 out. And you got, so this is the side length, this is the area, and the area, it depends on the side length. The area is a function of the side length. You put in 3 into the area function, you get out 9. Other examples, the height of a projectile depends on time, yearly sales of a product depends on time, temperature of a component depends on how long it's been used for. We've got stuff about beams. The speed of or velocity of an object depends on time, the acceleration depends on time, etc. We've got all these different examples. There's an example there from the top of the page from electronics. So if you've got a circuit with a fixed resistance, the current depends on voltage. So current is a function of voltage. The population of bacteria depends on time. Hooke's law says that in a spring, the force is a function of the displacement. For example, the displacement of a spring is a function of time. And then, of course, you can always, as I say, you always plot these things. So if you say here, you say displacement is a function of time, you put the function output on the y-axis and the function input on the x-axis. I got a few more there. Okay. Now in this chapter, what we're going to be more interested in is functions of several variables. Now, you can think of that as that's got a number of inputs, but that's not really the way a mathematician would think of it. A mathematician would just say that the input is more than one number comprises the input. Similar story really to vectors. Like vector is a single object and a pair of numbers is a single object. Okay. Now the one we're going to think about for a second is the bending moment on a light beam. So this is the bending moment is a function of x. Now x is the distance along the beam, and if it's simply supported, the bending moments at the ends are 0. I'm not actually sure how much you know about bending moments, but the bending moment is a function of the distance along the beam. So if you want to think in terms of inputs and outputs, take a distance along the beam, say 2.5 meters, and the bending moment at that point is an output. So this would be, say, 2.5 along the beam, and then the bending moment there, like that. So bending moment is a function of a single variable x. Now, what we want to say is that in general, things can be more complicated. They can be you can have functions of several variables. So you've got a variable that depends on numerous other variables. A very simple example would be the bending moment on a square plate. That depends on two variables, because to specify while with a beam, to specify a point on the beam, you only need one number. To specify a point on a plate, you need two. And so the bending moment on a plate depends on two variables. It's a function of two variables, and we write it like this. Bending moment is a function of two variables. And these are the kind of things that we're going to study in this chapter, functions of several variables. Most of the time we're going to concentrate on functions of two variables. So for example, now z would, instead of y depending on x here, we'd have z depending on x and y. So the input would be x and y, the output is x squared plus y squared. The input is x and y, this is the output. But most of the things we do will generalize if you've got more variables. So we're going to see a few things in this list where you have a function of several variables, a variable depending on multiple other variables. Okay. So a simple example is the area of a rectangle is a function of two variables. It depends on the width and the length. So you can write that area is a function of width and length, and indeed there is a little formula for it. The area of I think I said area of a function. Area of a rectangle is a function of width and length. And there's a little formula here. The area of a rectangle with width w and length l is w by l. For beams, you have that the slope of the beam, and the deflection. So if I just draw a beam here for a moment. So this is supposed to be, actually if I could rub that, okay, I can't rub it out. So suppose you have beam and it's supported here, it's got two supports, and there's a little bit of a bend in it because maybe there's some kind of an applied load which causes the beam to bend. So there's two variables that I'm looking at here. The first is the slope. So the slope is basically, look at the beam, write down the tangent, and the slope, if this is the point x along the beam, from here, then this would be the slope at that point, would be the thing. The deflection, meanwhile, is the difference between where the beam is and the neutral. So at a different point, this distance here, this would be the deflection of the beam. Now, in general, you think of both the slope here and the deflection as functions of a single variable, the distance along the beam, but you could think of them as a function of several variables. The other variables being basically what the beam is made out of, and that's the material. That's where the E comes in. It's the Young's modulus. So how stiff is the material of the beam, and I is the cross section of the beam. So it's kind of saying that the slope, so fix the length here and have different beams. The deflection depends at each point on how far along the beam you are, the material that the beam is made out of, and the cross section, something like this. We saw an example in the previous thing where I said the current was a function of voltage, but that was keeping a fixed resistance. So you were varying the voltage, varying the battery as it were, but keeping all the resistors the same. In general, if you've got a voltage and a resistance, you can vary both of them. And the current depends on both of them. So current in a circuit depends on voltage and resistance. It's a function of voltage and resistance. Similarly, the volume of a cylinder depends on radius and height. And these are all very familiar things. So these kind of things happen or occur in engineering all the time. Now, the thing is, if you're graphing a function of two variables, now if you think of graphing a function of three variables, you get into problems. You can use color and stuff, but we'll just imagine functions of two variables. You can plot these. They're going to be in three-dimensional space. And we'll see, for example, why is that? So say, for example, you talk about this is the x-axis, this is the y-axis, and up here is the z-axis. If you put in to this function 1 and 2 in, you'll get 1 squared plus 2 squared, which is 5 out. Say 1 along the x, 2 along the y, 5 along the z. And because there's two numbers are kind of in the input, and then there's one number in the output, this is kind of the same as 3 numbers. Now, mathematically, you kind of say, oh, there's just an input and output, and the input happens to have 2 numbers, but of course it's far more natural to look like this. And of course 3 numbers is a point in space, and if you look at all the points of the form input, output, they're all going to be have 3 dimensions. So if you plot all of them, you're going to get some kind of what we call a surface. So the graph of a function of 2 variables is what we call a surface. Okay. Now there's a little thing down here saying, oh, why are we looking at this as engineers? I think a lot of the examples that we've looked at show that functions of several variables are going to be important. Here there's just a little thing on the bottom if you want to read it. It just kind of says what are the kind of problems you'll be able to solve using the methods of this chapter. Now actually both of them are a little bit beyond what we're going to look at, but to give you an idea what we could be looking at. So this is the start of it. We're looking at functions of several variables, and we're going to be thinking about the graphs initially, and the story is that the graphs of these things are three-dimensional.